Good morning, everyone.
Morning, Professor.
Excited about learning some cool law like the law of Biot-Savart today. It's awesome. You don't sound to be bubbling with enthusiasm. It's going to be so cool, I tell you. Actually, the Biot-Savart law is really one of my favorite, even though it's really, complicated and crazy looking, but it's pretty awesome.
Hey, I got a question.
Go for it.
So I see two midterms that you posted, and one goes from 21 to 30, and the other is 21 to 26.
The 21 to 30 is not supposed to be there. I don't even know how it opened, so that's a problem. But yeah, don't mess with that one. I don't know why it's there. Let me go back.
Yeah, because it expires tonight, so I wasn't sure what was happening with that one.
Gotcha. That's crazy. I don't even. Well, sometimes I use the roller on my mouse, and sometimes that will roll beyond where I put it, and then yeah, there it is. I see it now. Yeah, that's crazy. It says midterm 21 to 26 midterm. Yeah, that's not even supposed to be there at all. Well, good. Nobody's taking the wrong one, so that's a good sign. And
Oh, I kind of panicked when I saw the 21 to 31.
yeah, it's always supposed to be 21 to 26. Actually, I would have preferred to make it 21 to at least 28. But that brings me to the other question I had for you guys. I've moved my midterm for my Monday and Wednesday class. I moved it to Monday instead of Wednesday. Would you guys want to move that to Tuesday, or do you still want to
Tuesday sounds great, actually.
Yeah, that would work.
No.
Yeah, more time would work. So
Okay. Well, today we're going to do chapter 28. Would you still be cool with it if it included chapter 28 as opposed and 27 instead of just 1 through 26?
I prefer if it stick to 21 to 26.
Okay. Yeah, I can do that. All right. Well, we'll make that official then. We're going to officially have the midterm a week from today, and it'll be 21 through 26. Maybe I might throw in 27, but I doubt it. So that way, I'd have to make up a whole nother practice test and all that good stuff. So I think 21 and 26 will be fine. That does make the final a little bit longer, but anyways. So everybody get that. We are moving the midterm. It's 1 week from today, and today is the 12th, so that'd make it the 19th. So wait for Krista to come in. So our midterm will now be on the 19th, and remember our class starts at 11, and I'm giving you a full 2 hours to take it. So you either need to be prepared to start at least 45 minutes early or to finish at least 45 minutes late. Okay. If you start after 11, then you're not going to get your full 2 hours period. So you got to make sure you guys start no later than 11. But I'm going to open it up about 45 minutes early and leave it open for an extra 45 minutes after class. But each of you are only allowed 2 hours to do it. So it's 120 minutes. But if y'all have a problem, like if you have a class immediately before and immediately after, you need to let me know so we can set up. I'll make an entirely different one for you and do it then. No, I'm not going to change. Yeah, I'll change well, I don't have a window set for the regular practice test that you're supposed to do multiple times. I do have one for the respondus one, and I really want y'all to get that respondus one done now. So you shouldn't be waiting any longer than that. It should have been done.
The practice midterm we put up is also 21 to 30.
Ooh, that's not good. It was not supposed to be. Let's see. Maybe it's just mislabeled. Let me double check real quick while I'm here. Practice midterm 21 to 30. Let me look and see if I did do chapter 30 questions. I seem to remember going in and changing it to just 26. Let's see, I got No, it just says 30. It doesn't include 20. It doesn't include 27, 28, 29, and 30. So we're lucky. I'm going to change the name real quick so it won't look so bad. All right. And that one you have basically until just about the last day of class to do. All right, so that's set up. So our midterm, excuse me, will start, like I said, it'll open up about 45 minutes before 11, and it'll close about 45 minutes later than class ends, which is what, 12:15. So that'd be about 1 o'clock is when it ends. So make sure y'all can start early or stay late, one of the two. If you can't, let me know, then we'll have to set up something different, a whole nother test for you guys, in other words. Okay. Anything else
And
before we get started?
just to clarify on a technical question, so we aren't having class that day because the respondents is going to knock out Zoom, so we would only have the test, and then that's it.
Yeah, yeah. And I'm trying to keep it on Mondays and Tuesdays, so you won't be a day that you're having a lab. Okay. Yeah. So, like I said, the responders practice midterm, you need to go ahead and take that immediately, like today. Okay, if you haven't already taken it. But the other one you can take as many times as you want. That one you can only take once, but the advantage is you get to see the right answers. If you get one wrong, or if you get it right, you get to see that it's right. So let's go ahead and get started then. Does anybody have any questions on anything before we get started, material wise? All right. So what I'm going to do is turn on my document cam, and I'm going to introduce you to a new law. It's called the law of Biot-Savart, or the Biot-Savart law. So the Biot-Savart law, and it's normally hyphenated, and it's SAVART law, basically says that the magnetic field is equal to mu0 I over 4 pi times the integral, and here's where things get crazy, of dl cross r hat over r squared. And that r hat's kind of a pain, but you got to know what it refers to. So if you imagine a little piece of wire running along like this, and say you want to know the magnetic field, let's say the current is going this way. So I is going this way into there, okay? And we want to know the magnetic field at this point P, right there. Then we break this wire up into little segments DL that are tangential to the wire and go the same direction as the current. And that's our DL vector. And then our R vector points from the DL to the actual point in question. Okay. And of course, when we say R hat, what we mean is you're going to take that and divide it by its magnitude. So you'll have that value. Okay. So that looks kind of nasty. And by using the R hat, it makes it where you could otherwise use a regular R and just put an R cubed down here like we did with the Coulomb's law. But this actually gives the vector form of the magnetic field. So the first thing I want to do is I'm going to consider a specific case. So let's say this is the x-axis. Let's say this is the y-axis. And then, of course, that would mean the z-axis has to come out of the page like this. Okay. Now let's imagine a wire that's infinitely long running along the y-axis. Like so. And it's infinitely thin. So I don't get a pesky negative. I'm going to stick a pesky negative in the beginning. So I'm going to say the current is going down. So I is just this quantity and it's going down. Okay. What I'd like to know is what is the magnetic field right here at point P, which I'm going to say is a distance R away. Okay, so even that's on the x-axis, I'm just going to call that distance R so we can get a formula in terms of R. I could do it in terms of X and then change it to R later or something for it to be more generic. But right now, I'm just going to say this X value has a value equal to R, okay? So what we do is we calculate DL. Well, DL is supposed to be a vector, infinitesimal vector along the current carrying wire pointing in the direction of the current. So in fact, DL should be negative dy times j hat. Does that make sense to everyone? So we're going to do like this little bit right here, say. And that's our DL. Okay. The I is the actual current that we have written there. Now what we need is the R vector, which points from the wire. So if this is up a distance Y, for instance, it's going to point from Y to this point. So that's our vector R. So you can see R has a negative Y component and then a positive X component equal to R. And that's the R, the magnitude. Okay. So actually, since that's, let's go ahead. I'm going to go ahead and call it X instead of R. Go ahead and change that, everybody, just because I can see some crap coming from it that'll make it a little bit more confusing. So we'll just change this to X and stick with that. I will change it at the end, but you'll get a very simple formula. You've already seen it before, but we'll say this is X and this is Y. So you can see the R vector, in fact, goes down Y and then to the right X. Okay. So that means that R is actually equal to X I hat minus Y J hat, and that the magnitude of R, which is just R, is equal to the square root of X squared plus Y squared. Okay. So B, according to the Biot-Savart law, is mu 0 I over 4 pi. And by the way, mu 0 is 4 pi times 10 to the negative 7th. And that's in Tesla meters per amp. Okay. You can find that as one of the constants in the front cover of your book. Yeah, that's just called mu 0. Just double check and make sure I had everything right. So that's what that is. So now we can say mu 0 I times the integral of DL cross R. So I'm going to go ahead and write this in here, and I'm going to say negative dy j hat, and that's going to be crossed with R hat. So R hat is going to be X over the square root of X squared plus Y squared times I hat minus Y over the square root of X squared plus Y squared J hat. And then all of that, of course, would be divided by R squared, which is X squared plus Y squared. So everybody see, I just realized this part of the screen was not even showing to you guys. So you see, you're going to integrate this basically from negative infinity to positive infinity because it's an infinitely long wire. And it looks really like a nightmare right now. But just like the dot product, the cross product's also a linear operator. So I can do this linear operation right here, and I'll see that j hat cross I hat, or negative j hat cross I hat. Negative j hat would be downward, and cross that with I hat, that would be in the positive z direction. So basically this part with this part ends up becoming positive k hat times x dy over x squared plus y squared to the 3/2 in the bottom. Okay, and that all will be in the k hat direction. This one, on the other hand, is j hat cross j hat, and that of course gives you 0. So I can now make the simplification that the answer is mu 0 I. This x is a constant, so I'll pull that out in front. over 4 pi times the integral of dy k hat, and k hat, by the way, can come out front because I hat, j hat, and k hat can always be pulled out in front of an integral or a derivative. And this would be x squared plus y squared to the 3/2 power. Okay. So if I let y equal to x tangent theta, then dy is equal to derivative of tangent is secant squared d theta. Actually, yeah, x times that. So is everybody familiar with that derivative, or that integral, I should say? I'm going to double check myself just to make sure. I think the integral of, or excuse me, the derivative of tangent is secant squared, and I'm about 99% sure that's right, but for a second I wanted to write cosecant. I'm pretty sure that's the cotangent. Anyone confirm that for me? All right, we're going to go with it and see what happens. So the dy basically that I need, or that I have, is already x secant squared theta. So what's going to happen is I now have mu 0 I times x squared over 4 pi times the integral of, I've already pulled this x out in front. I get secant squared theta d theta. That's what the dy became, k hat as well. And then all of that will be over x squared, which I can factor out and make it 1 plus secant squared, 1 plus tangent squared, excuse me. 1 plus tangent squared theta. And all of this, of course, would be to the 3/2 power. So this becomes, again, now 3/2, and then x to the square under that. The 2 multiplied by the 3/2 just gives you cubed. So I get mu 0 I, x squared over x cubed just becomes over 4 pi x, like that. And I get the integral of secant squared theta d theta k hat over 1 plus tangent squared is secant squared, but secant squared to the 3/2 power is secant to the 3rd power. So this is secant cubed theta, like that. And of course, that means 2 of these babies cancel out, leaving just secant in the bottom. And of course, secant in the bottom is the same thing as cosine on the top. So I can say equal to mu 0 I over 4 pi x and the integral of cosine theta d theta. Now, notice when I said at y equals x tangent theta, what that means is there's x, there's y, and there's theta. So as y goes to infinity, which is the top range of integration, theta goes to 90 degrees. Similarly, as y goes to negative infinity, theta goes to negative 90 degrees. Okay. So the derivative of sine is cosine. So the integral of cosine is just sine. So I'm going to say mu 0 I over 4 pi x times the sine of theta. And of course, theta being 90 is pi over 2. So negative pi over 2. We remember, of course, our sine theta looks like this. And it's an odd function. So we can see This is pi over 2 right here. And this is negative pi over 2 right here. So I can say, again, I got a k hat out there. I can finally say sine of pi over 2 is obviously 1. So I'm going to say mu 0 I over 4 pi x times 1 minus sine of negative pi over 2, which of course is negative 1. So I get 1 minus negative 1, which is of course 2. And then 2 times the 4 gives me 2 pi. So the ultimate answer is mu 0 I over 2 pi x, which is exactly the formula I told you before for the magnetic field due to a wire. In fact, the magnetic field due to a wire is given by mu 0 is given by B equals mu 0 I over 2 pi r, where r is the perpendicular distance from the wire. Okay, and it's given directions given by a right-hand rule. Right-hand rule. Okay, and what it means is basically, hey, if I grab the wire with my right hand and my thumb pointing in the direction of the current like I do here, then my fingers curl around the wire in the direction that I expect. So that means back behind there on the negative z axis, it'd be pointing to the right. Right here, it'd be pointing straight out, which is why we got the k hat here, exactly what we expected. Out in front here, it'd be pointing to the left, and then over here, it'd be pointing into the page. Okay, so I often use something like a phi hat or something like that to represent it. But again, that all depends on how you set up your coordinate. But that is the general result, and that's exactly the one that we wanted to get. And in fact, when I show you Ampere's law, you'll see a much easier way to get that. So this is an equation that you can use repeatedly. B equals mu 0 I over 2 pi r. You just have to remember the right-hand rule, which you say like this. Let's say the current's going this way. Then that means out here in front, it's going this way. To the right, it's going into the page. Back here, it's going this way. And over here, it's coming out of the page. So basically, a line of constant magnetic force is a concentric circle. Okay, hopefully that's enough for you to remember how the direction goes. So any questions on that? That's the law of Biot-Savart, and as you can tell, it's not a trivial law to implement. It's kind of a complicated thing to do, but it is something that we can do. So, for instance, if you wanted to take, let's say, as another example, example 2. Let's consider another configuration that the law of Biot-Savart helps us with. So let's imagine, for instance, that I have an XYZ coordinate system. There's my X, there's my Y, and Z is coming out of the board. Okay. Now let's imagine that a wire is running this way and then makes a semicircle and goes back out this way. Okay, let's say that radius of that semicircle is r, and the angle, of course, is, or excuse me, the thickness of the wire is really negligible, but the current is in fact going this way. What I'd like to do is calculate the net magnetic field right here. So according to the law of Biot-Savart, B is equal to mu 0 I over 4 pi times the integral dl cross r hat over r squared. So I'm going to break it down into parts. One part will be this little doohickey right here. Another part will be all this. And then the third part will be this. So this is part 1, part 2, and then part 3. Okay. So let's look at part 1. What I'm going to say is DL is this little thing, and it points this way, and it's going to be negative dx I hat. Okay. So DL is equal to negative dx I hat. And then R hat, or R, excuse me, R is going to point from here to there. So you can see R is some value, let's say X, and it points in the positive I hat direction, where this distance right here is X. And the X is actually going to go from, let's say, from R to question mark. In other words, this wire might go on forever. I don't know. But the main thing is it doesn't start till there. But you can immediately see that DL, which is in the I hat direction, crossed with the R hat, which is going to be in the I hat direction. That's going to give you 0. So you can automatically see that DL cross R hat is equal to 0. So there's no magnetic field there. Now I'll do part 2. And in this case, we're going to say DL is equal to positive dx I hat. And R, of course, is going to be some negative x I hat. So again, these two tell you that DL cross R hat is going to equal 0. So no contribution comes from the magnetic field for these two straight pieces. So that leaves us, I called that part 2, but I meant it to be part 3. Sorry about that. So now let's look at part 3, which is the big deal. Okay, it's the main part that actually gives us something. So part 3, what I'm going to say is this will be DL, which is in fact equal to R times d theta, and it points in the theta hat direction. In other words, that direction right there is the direction that theta increases. In other words, always perpendicular to a radius vector. Okay, I can work out d theta if I really wanted to, or I can work out theta hat if I really wanted to. Let me show you what it is. If, for instance, this is the x-axis and this is the y-axis, this would be r and this would be, say, theta. Then what you can see is I put my x-axis over here. This is going to be perpendicular to that. That's actually theta hat. Okay, you can see that this angle right here is theta, which means this is theta, which means this is also theta. So theta hat would actually equal, once I notice that I have to divide out the magnitude, it's basically its x component is going to be, its x component is going to be negative sine theta I hat, and its y component is going to be cosine theta j hat. And you can tell that has a magnitude of 1. Generally speaking, it'd be like r sine theta or something like that. But then when we take the magnitude, we get that. So that's really what it is. But you don't really have to think about it more than just as a convenient little thing to use. So I now know that DL is going to be r, the radius of the arc, d theta, theta hat. And I also know that r vector is just going to be r time, or excuse me, big R. Remember, it points from DL to here. So that's my R vector is pointing this way. So my R vector is going to be negative R in the R hat direction. Now we could also figure out R hat up here. R hat would be that little guy. And of course, that's cosine theta, sine theta. So R hat is equal to cosine theta I hat plus sine theta J hat. And in fact, if you take dr d theta, dr hat d theta, you actually get theta hat. So that's another nice thing to remember. So if I take the derivative of R hat, I actually get derivative of cosine is negative sine, boom. Derivative of sine is cosine, boom. So now I've got what R is. Not that I'm necessarily going to use it, but in some sense, if the vectors stay, then yeah, you'd have to integrate them. And the only way you can integrate them is interpret them in terms of I and J. So I've got that. And of course, that means that R hat is just going to be negative R hat, which is a really inconvenient thing. But what we're saying is the R hat that goes on this side of the formula is the negative of the R hat from cylindrical coordinates. Does that make sense to everyone? So sorry about using the same symbol here. Maybe I can say BS for Biot-Savart, and that would be BS. And that would be BS in this version. That would, sort of make it okay. All right. So now all we have to do is compute B at the center. So B is equal to mu 0 I over 4 pi times the integral of R d theta theta hat crossed with negative R hat over R squared, because remember R is the distance from it, and that's going to be that capital that big R. So when I do this, I can see for starters this R and this R are constants, and one of them cancels out on top, so I'll get mu 0 I over 4 pi R like that. And now theta hat cross negative R hat. Well, theta hat points this way, negative R hat points this way, so I can curl my fingers this way and I see it points out of the page, which is the K hat direction. So in fact, I'm going to get mu 0 I K hat. That comes from the cross product, and all I'm left with is the integral of d theta from, of course, theta equals 0 to pi. Okay. So the integral of theta from theta equals 0 to pi, or the integral of d theta from 0 to pi is just theta evaluated at pi minus theta evaluated at 0. So that's just pi. So I'm going to get mu 0 I over 4 times R in the K hat direction. And that is consistent with the right hand rule. Remember, if we grab the wire with our right hand inside the middle, my fingers are sticking out of the page. So that's exactly the direction we expected. Any questions on that? So that's a pretty tight one. Let's try one more with Biot-Savart. This will be example 3. And what I'm going to do is I'm going to imagine an XYZ coordinate system where X is coming out of the page. Then Y is over here. And then Z is up there. And what I'm going to do is I'm going to have a complete circular loop of radius R lying in the XY plane. So I'll say that's a circle of radius R. And I'm going to say it has a current running around it in this direction, I. Okay. So again, I can say this might be the angle theta, and this might be the angle d theta. So that DL is just going to be equal to R d theta. Okay. What I would like to know is what is the magnetic field at this point right here, which is up some distance, say Z. Okay. Well, what we can see is basically the R vector would have, if I draw it a little more clearly, you might see that this would be a leg of the vector, and this would be another leg of the vector, and the vector which runs from this to the point in question would be this figure right here. So that's the R vector. Now this distance is Z and that distance is R. And in fact, if I really wanted to, I could put my y-axis there, put my x-axis here, and you see that this is theta. Okay. So really what we're saying is this is our XY component and this is our Z component. Okay. Now that might not look so nice, but that's okay. We can say this is in fact negative R, because it's pointing inward, times R hat. And this one's just ZK hat pointing upward. So the R vector is just negative R hat plus ZK hat. That's really everything about it, but we don't have to really get all that fancy, especially if you notice some things about the situation before you write all that. For instance, the Biot-Savart law says B is equal to mu 0 I over 4 pi integral DL. So the DL is R d theta, and it points in the theta hat direction. I forgot to write that earlier. So that's a theta hat direction right there. And then we're going to cross that with the R hat. Well, the magnitude of this is just R squared plus Z squared square root. So the square root of R squared plus Z squared is the magnitude. So really, if I wanted R hat, I would write it as negative R over square root R squared plus Z squared. R hat. Again, I'll write this as BS for Biot-Savart, so we won't confuse it with the actual radial component vector, plus Z over square root R squared plus Z squared in the K hat direction. So when I write that over here, actually might have got it worse that time. When I write that over here, that's going to become negative R over that square root, blah, 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 R hat plus Z over that square root, blah, 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 K hat. So theta hat cross R hat, you can see immediately theta hat cross actually negative R hat. That gives me a K hat direction. And then when you take theta hat cross K hat, theta hat is like this, cross it with K hat, and you get something that points radially outward. Basically, you get an R hat vector. And the R hat vector, I think you can tell, pointing out this way, it's going to have a diametrically opposed one over this way. And by symmetry, that means this component should go to 0. Another way of thinking about it, of course, is R squared plus Z squared. You can see that this is basically sort of an even function, and we're going over the whole angle d theta. So the fact that it points this way here, 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 all of that's going to cancel out, and all we're going to have left is just that K hat one. So we can use that symmetry of the problem to recognize that this integral goes to 0. Okay, you don't have to do that. You can actually compute it out if you wanted to, but you'll see Z squared, R squared, and Z squared, they're all constants. They're going to come out in front. So it's really not going to matter that much. Excuse me. No, not that one. I was saying that the other one. Sorry about that. Well, actually, let me work it out. Theta hat cross K hat. Yeah, so theta hat was this way, and I cross it with K hat. Yeah, that's going to be in the R hat direction. So yeah, that's the one that's going to cancel out. Okay. So all I'm left with is mu 0 I R over 4 pi times the integral. Now, theta hat cross negative R hat, we did work out was theta hat cross negative R hat should give me K hat direction. So I'll put a K hat right here. Okay. And then all I have is the integral d theta from 0 to 2 pi. So we can tell that's in fact mu 0 I R. Oh, I forgot over the square root thing. Like that. Over 4 pi times the square root R squared plus Z squared. So that all came in front, and then I got a K hat. And then I got the integral d theta is just 2 pi. So I'm arguing that the actual answer for this is B at Z is equal to mu 0 I R over 2 times the square root R squared plus Z squared. All of that in the K hat direction. Now, if you wanted to confirm that, what you'd have to do is you'd have to say, you'd have to make a theta hat what it is. So let me take a second and confirm with you that this is really going to integrate to 0 mathematically without symmetry. So what I'm going to say is R d theta is the magnitude. Of course, theta hat we learned was negative sine theta. So I'm going to say negative sine theta I hat.
Oh, we can't see.
Oh, sorry. Thank you. I'm going to say negative sine theta times the RD theta, which is what I had there. And then up here, we see it was also cosine theta. So I'm going to say plus R d theta cosine theta, J hat, and then 0. And then I'll put I hat here, J hat here, and K hat here. And then that's the first part of the cross product. The second part of the cross product, of course, is just Z over the square root, and that's in the K hat direction. So I shouldn't even have the K hats inside the matrix. I just decided at the last minute to go ahead and put it in the matrix. So we can get rid of that. This is going to be 0. This is going to be 0. Now we got to take the determinant of that to determine the cross product. If I do expand on this minor, then I'm going to say the answer is I hat times, notice this is 1, 1, first row, first column. So -1 to the 2 power is -1 squared. So that's just +1. So I don't have to do anything special, but I do have to hide this column and this row, which means I just do this minus this. So I can see R d theta cosine theta times Z over the square root R squared plus Z squared. That's all in the I hat direction. Okay. And then of course minus 0, but that doesn't matter. Now I'm going to do the J hat term. This one's an actual 1, 2. In other words, row 1, column 2. So that'd be a -1. So what I'm going to do is do my determinant in the opposite direction, and that'll correct for the minus. So I'll put a J hat here. And instead of going like this minus this, we're now covering up this column and this row. So I'm going to go 0 times 0 minus this times this. And we'll see minus times a minus gives you a positive R d theta sine theta Z over the square root R squared plus Z squared. And that should be the whole thing, right? And then of course, when you get to K hat, you can see that covering up this one and this one, I'm going to get 0 and 0. So nothing comes from that. So now what you see is you're going to integrate cosine theta, because that's literally the only thing in theta. you're going to integrate cosine theta from 0 to 2 pi. Well, cosine theta looks like this. Clearly, the integral of cosine theta, this half and this half add up to give you the same as that, but it's on opposite sides, so that's all going to be 0. And then similarly, when you do sine theta from 0 to 2 pi, this half is positive, this half is the same side as negative, so this one should also be 0. Again, because the r, the z, and the square root of r squared plus z squared just comes out in front. So you're just integrating sine theta d theta and cosine theta d theta. So that's why it actually did cancel out mathematically. Physically, we made perfectly good sense of why it canceled out, but not mathematically. So now we've done it mathematically as well. So does anybody have any questions on that? Thanks, Aiden, for confirming that my derivative was correct. Secant squared theta. So this is nasty, right? This is the most horrible mathematical problem you've ever seen, right? Doesn't it make you want to cry and go home and consider quitting? That is not a abnormal scenario. Most of the problems we do will be like this variety, like you can do this one. Maybe you go for 45 degrees, then you go out another radial line and there'll be another radius. And then you can come back in and do a different radius even than the first and stuff like that. You can do a lot of different problems like that. And they're all going to reduce to the same simple stuff where it's like mu 0 I over 4 pi r times some angle, right? And then that angle is going to cancel out the pi's and all that good stuff. So don't be afraid of it. Other than doing that infinitely long line, which is very much analogous to the first integral we did in this class. Remember the very first day when we did Coulomb's law and we had a string of charges along the z-axis or the y-axis, and we calculated the electric field there. This is just like that, except calculating the magnetic field there. So that and this are really the only quote unquote, and this are really the only quote unquote difficult Biot-Savart laws. All the other ones will be things like this, and you can find them at the end of the chapter if you want some extra practice. Not only that, the practice test, when you start doing that for this chapter, you'll see there's a lot there as well. And they have a couple in the homework. I didn't like how few they had, but it'll do. So that's the nastiness of it. That's what you actually get. And yeah, that's kind of cool that you can do it at all. But as you can tell with that nasty of a formula, really to solve a physics problem that way is going to take a computer. So luckily we came out with another version, and this is called Ampere's law. So now we'll say Ampere's law. And Ampere's law is it's the magnetic analog to Gauss's law. Remember, Gauss's law was the closed integral of E dot dA equals Q enclosed over epsilon naught. Well, Ampere's law is the closed integral of B dot dl. Notice that's a line integral as opposed to a surface integral, but that's supposed to be equal to mu 0 times I enclosed. So before we made a Gaussian surface around some charge, and we chose that Gaussian surface so that everywhere on it, the E was perpendicular to the dA and therefore constant, or the E and the dA were both parallel so that part of the integral would disappear. And by so doing, you could solve for this E, even though it's the integrand in an integral. We're going to do something similar with this. We're going to create a Amperian loop. So it's a circle or a semicircle or something like that. It's actually got to be a closed circle. So it can be like a circle or an oval or something like that, such that everywhere along that circle, B is going to be a constant, or B is going to be perpendicular to DL, in which case it wouldn't matter. And then I enclosed is just the current that goes through that loop. So let's take the example we just did with the law of Biot-Savart. So let's say we have a current carrying wire carrying a current I downward. Okay, I'm going to again put this along. In this case, I'll call this the x-axis. This case will be the y-axis. In this case will be the z-axis. Okay, what I'm going to do is imagine an Amperian loop. So what I know is basically the electric or the magnetic field caused by this wire has such a symmetry such that if I maintain a concentric circle, I should have about the same strength everywhere. So I'm going to make a concentric circle be my Amperian loop. Like this. That's my Amperian loop. And the reason I chose that again was because I knew from the symmetry of the physics problem that if I set the R equal to a constant, I'm equally far away, and therefore the magnetic field shouldn't change. It should in fact be a constant on there, and in fact should be parallel to this if I integrate in the proper order. In other words, DL is going to be just R. Well, let's use a lowercase r. Is just going to be R d theta, but in the theta hat direction like we've been using before. And I'll make my hypothesis. I'll say B is equal to some B as a function of R only in the theta hat direction. Okay. So the left-hand side of Ampere's law is the closed integral of B dot dl, which is equal to the integral of B of R times theta hat dotted with R d theta, and R, by the way, is just this radius right here, R d theta, theta hat, which again, the dot product's a linear operator, so I can say the integral of B of R times d theta, theta hat, excuse me, dot R hat, or excuse me, theta hat dot theta hat, which of course this is 1 times the cosine of 0, so that's 1. And again, we're looking also at the fact that R is in fact a constant. So B of R, since it only depends on R, that should be a constant. So I can say this is B of R times the integral of d theta from theta equals 0 to 2 pi. So I get B of R times 2 pi R. That's my left-hand side. Now my right-hand side, what you're sort of thinking is you're looking for the current that's enclosed in that loop. Well, there's a current that's clearly running from here right through the middle of that, and that current is just plain I. You can sort of imagine all the surfaces that could be spanned by that thing, and obviously the flat one is the obvious choice, but you could also have one really bubbly and stuff like that. And that's really what Ampere's law says, is that any current that goes through something spanned by this is going to count. So the right-hand side is mu 0 I enclosed, which is just mu 0 times I. So left-hand side equals right-hand side is easy peasy now. We can say B of R times 2 pi R is equal to mu 0 I. So we can find that B, which is actually B of R theta hat. Solving this for B of R, I get mu 0 I over 2 pi R theta hat. And that is exactly what we got earlier when we did it with the law of Biot-Savart. Any questions on that? So that's how you use Ampere's law. Kind of cool, right? Now that was example 4. So let's try example 5. Okay, so say we want to do example 5, and we have very specific symmetries that work really nice for us. So an infinitely long straight wire is a really good symmetry. Another one would be, for instance, a solenoid. You might recall that a solenoid is in fact basically just a electromagnet with a nail pulled out. So you remember making a electromagnet when you're in grade school, and basically all you did is you took and wrapped a wire around a nail and you connect the wire up to a battery, and then the nail became magnetic. Well, that's essentially what a solenoid is. So I can imagine ... like this, and these are all currents coming out of the page. That's why I drew the dot in the middle like that. And then over the other side, I got the same thing. Only, of course, these are currents going into the page. So really what you're thinking here is maybe this wire comes from over here like this and then goes down to here. And then this wire goes up to here and then goes down to here and up to here and down to here and up to here and so on and so forth. So it's really just a coil of wire. Now, according to the right-hand rule, if I grab this with my right hand, these wires coming out, you can see that in the center, the magnetic field, let's say just this one, the magnetic field here is here, the magnetic field here is here, the magnetic field here is here, and the magnetic field here is here. So it's going around like that. Well, guess what? The one next to it is going to cause something that cancels that one out in between the wire. And same thing with this one. And this out here is going to be so weak because all these are all contributing to a bunch of magnetic field lines going this way. So that's the net effect, is you have just one big strong magnetic field that probably doesn't vary very much from one side to the other. And in fact, B is approximately 0 out here. And what we need to do is find us an Amperian loop. So I'm going to take my Amperian loop to be, it's going to be any closed surface you want. So I'm going to do like that, and I'm going to integrate it around this direction so that when I get down here, of course, I'm actually parallel to the magnetic field. So in doing that, let's switch to blue. I don't want to write in black right now. So let's say left-hand side. The closed integral of B dot dl. Okay. Well, what I'm saying here is B is equal to, let's say B of y, because I'm going to imagine a y-axis, say right here. And I'm going to imagine an x-axis right here. So B of y I hat. And that's inside, but it equals 0 for let's say y greater than the radius of the solenoid. So if the solenoid's radius is r, then for y greater than r, it's going to be 0. And also for y less than, of course, negative r, it's going to be 0. So that's our hypothesis of what the magnetic field should look like. We think it's going to be fairly uniform. Maybe it depends a little bit on y. We're not really sure. And what we're going to see is that there's a couple parts. I got part 1 here, then part 2, then part 3, and then part 4 of the line. So this is going to be the integral over 1 plus the integral over 2 plus the integral over 3 plus the integral over 4. That's what that complete circle is going to require. Well, the integral over 1 basically is B, which is approximately 0, dotted with negative dx I hat. Okay, so that's the integral over 1. the integral over 2, probably you're going to have most of the b component, if it exists at all, is going to be more or less parallel to the x-axis. So you're going to get something like b of y, which is approximately 0, pointing approximately in the negative I hat direction, dotted with, in this case, you're going to say negative dy j hat. Well, a dot product between j hat and I hat is going to give you 0, even if that's not 0. So even if the magnetic field isn't 0 there, you're still going to get 0 because it's going to be more or less perpendicular. The integral over 3, that's the big deal one there. So that's going to be b of y I hat dotted with dx I hat, and then plus the integral over 4 is going to be basically, again, let's say a negative b of y I hat, which is on the order of 0, dotted with, in this case, positive dy j hat. So that one's going to be 0 anyways, because the I hat dot j hat is 0. And this one is essentially 0 because the magnetic field 0. So all I'm really left with is basically b of y. Well, that's a constant y, so b of y is going to be a constant. So it's just b of y times L, where I'm going to say this is the length from here to here is L. Now, the right-hand side is mu 0 times I enclosed. Well, if you know the number of charges, or excuse me, number of wires per unit length, you could say N is equal to the total number of lengths, or excuse me, the total number of loops divided by the big L, like that. So if this thing, the whole solenoid's length, was L from here to here, okay, then what we're saying is if you took that total number of turns and divided it by big L, that would be the turns per unit length. So if I take that N and multiply it by L, then that'll give me the number of turns in that little box I made. And then of course I have to multiply that by mu 0 times I times I, because the I is the current that's going through the wires. So now I can say left-hand side equals right-hand side. And that gives me b of y L is equal to mu 0 in Li. And you see immediately that the L's cancel out. Whoa, put the wrong top on my pen. The L's cancel out. And what you do get is B, which equals b of y I hat, is equal to mu 0 N times I. And that's it. That's the magnetic field of a solenoid. And that's the total turns. And that's the total length. Okay, so everybody sees that? Any questions? Y'all see how it's sort of like Gauss's law, that you're doing something that's in some sense very complicated, but it's actually quite simple just because we're using highly symmetric problems that make it work really easily. So in that sense, it's just like Gauss's law. But again, we're doing line integrals now as opposed to surface integrals. Any questions on that? We've done a couple now. We did the solenoid, we did the infinitely long wire solenoid, And now we can do, for instance, what time is it? Yeah, we got about 12 more minutes. Now I can actually do the toroid, which is kind of neat. So let's give an example for that one. So this is example 6. And this is this one was a solenoid, SOLENOID. This one's going to be a toroid, which, by the way, those of you who aren't in the know, but if you ever played what was it? Man, it was a video game. I want to say it was like Asteroids or something. I think it was Asteroids. Toroid is really the screen or the universe for the Asteroids game, because if you look at a computer screen playing that game, if you had, say, an asteroid go out this way, then it would come back this way, where this lined up perfectly with that. Similarly, if you had an asteroid, say, go this way, then it would come out right here. So what that means is this side is equivalent to that side. So we can go ahead and take like that. So you see that it's actually, this is the screen and it wraps around itself like that. But since the top is equivalent to that, that means it also does this sort of thing. The top's equivalent to the bottom. So ultimately what it does is this wraps around to that and makes basically a donut. Whoa, 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 whoa. Yeah, that one's supposed to be this. Okay. That would be like that. So really, when you were playing asteroids, you were playing on the surface of a donut. And that's what a toroid's called. So in this case, we're going to imagine in the XY plane, so let's say this is X, and let's say this is Y. We're going to imagine that we have a bunch of wires. And then another bunch of wires. And I'm not saying the wires are looping like this. I'm just being lazy. Really, like all these are supposed to be just like that one up there. So these are a bunch of currents, say, let's say going, if I did that, that would make that way. Yeah, that's fine. I'll say these are all currents going into the page, and these are all currents coming out of the page. So the easiest way to write that is draw two representative ones. So these currents are coming out of the page, these currents are going into the page, and basically it's a loop like that. So you basically took this solenoid and you made it long enough that you can bend it back on itself, and then you'd have a toroid. Because of that, we can see now that the magnetic field should actually be really, really uniform and should point along this direction right here. So that's the magnetic field. I don't know why I wrote current, I wrote B there, okay? And that's going to be our Amperian loop as well. So with that Amperian loop, we can say, all right, the left-hand side of Ampere's law is the closed integral of B dot dl. So I'm going to make the hypothesis that B is equal to B of R. And by the way, the radius of this thing is just big R. And that's sort of to the center of the coil of wire. It's going to be B of R times theta hat. And DL is going to be R d theta, theta hat. So I'm going to get B of R theta hat dotted with R d theta, theta hat. And of course, the B of R, since it's evaluated on the actual radius R, which I can write big R now, that can just come out in front and write B of R times R. integral d theta times theta hat dot theta hat, which is just 1. And I'm going to integrate this from 0 to 2 pi. So ultimately, I'm going to get just b of r times 2 pi r. Now, in this case, the right-hand side, which is supposed to be mu 0 times I enclosed, well, notice that's the total number of turns. And these current carrying wires, which are coming out of the board, notice their magnetic field wraps around in the same direction as BDL, so I can use a positive current there. If there was currents in there going the opposite direction, like inside of here, instead of coming out, it was actually another one going in, then I have to do mu 0 I this one minus mu 0 I the other one, because the current direction doesn't match the right hand rule that you're supposed to. So in this case, it's just going to be mu 0 times the total number of turns times I. So left hand side equals right hand side. That's going to give me b of r times 2 pi r, and I really should put a big R there, but it's just no big deal either way. And that's equal to mu 0 n times I, where n is the total number of turns. And then you can see that b is actually equal to mu 0 n I over 2 pi times the radius. And that points in the, well, I said theta hat, so I should stick with theta hat, not phi hat, the theta hat direction. So it's the same formula as for the single wire, but it has n times it because there's the n wires, and the r means something entirely different. It still means the distance away from the center, but it's not, there's not a lot of variance in R. You know, from this edge of the toroid to this edge, that's a very small difference. So the magnetic field's basically a constant equal to mu 0 n times I over 2 pi times that radius. So any questions on that? All right, so your book does a neat example, example 28.8. I definitely want you to check that out. So I'll mark it on here. Example 28.8. Basically, you can use Ampere's law to prove that you cannot have a uniform, well, a singly directed non-uniform magnetic field. So in other words, if you had a magnetic field that was everywhere parallel to itself, but it was stronger in one area than the other, like this, that's impossible. So you cannot actually have this. In other words, if you had this, you could do a line integral across here. That would be b times negative b times L. This would be 0, 0, 0. This would be a different b times L. And this would be 0, 0, 0. So I'd get minus BL plus BL. And those two would be different, but there's no current inside of it. Therefore, it must be equal to 0, since that term is 0. So the fact that this B would be weaker than that B, but they're both parallel, means that these two should cancel out because there's no current in there. But you can't cancel out because this one being farther apart than the others means the magnetic field's weaker, and this one being closer to the others means the magnetic field's stronger. So I got a big B times an L and a minus little b times an L, and that's supposed to equal 0. That can't equal 0 unless the b's are equal. So what you can have instead is you can have a magnetic field whose direction changes along with its strength. Like that. That's allowed. So that's the example that I wanted you to check out But it's pretty cool. I like the ability to show that or think about that. So you guys are free to go. If you have any questions, I'll wait around for the last of you to ask them. Otherwise, remember our final has been moved to Tuesday. Make sure you do the online respondus practice test immediately, because I think it disappears either today or tomorrow. I think it disappears tonight at midnight, and you need to take at least one attempt. It's not going to count as a grade for you, but whatever answer you get to see the right answer, and you get to find out how to, install the respondus lockdown browser and all that good stuff. So see you folks. Thanks for coming.
And just to confirm, there's only supposed to be one midterm, right? The other one was
Yeah,
mistakenly.
it's only one midterm. If you ever see more than one, that's usually because I've got another student I had to make one for, and I made it visible to everybody, but only one person could take it. So that's the same thing with all the other tests. If you ever see multiple tests, if you've taken one, you're good.
So a quick question about the midterm. Is it going to be mainly like I'm not sure if you can even answer the question just because of, fairness and whatnot, but is the midterm going to be more of application questions or derivation questions like this would be?
I call these application as well as derivation, but yeah, they're a lot of them are, well, you've seen how the practice test goes. It's just like that. So, a lot of them are using just symbols, but some of them use numbers. So it's going to be a little mixture of that. I think I made it where there's like 6 problems and maybe 4 or 5 concept questions.
Okay, so it should be about the same length as these practice tests, like the 9 to 13 questions-ish?
Yeah, somewhere like that. Yep.
Okay, thank you.
No problem.
Thank you.
You're welcome.
So just to make sure, like a last time, it's next Tuesday?
Yeah, I moved it when you were just coming into class. I asked the students if they were interested, and obviously all of them were. So yeah, I went ahead and moved it to next Thursday. If you've got something set up and you need to take it now, it's ready. So you could do that if you wanted. Tuesday if you wanted. We just have to set it up where you take it, and not during class, but some other time. So like if I've inconvenienced anyone, I'm willing to work with them.
And
Okay.
Professor, that's for the midterm, correct? Because it
Yeah.
still says that it's only available until tonight.
Yeah, that's the respondus practice midterm. The actual midterm is now gonna, the actual midterm will have a date associated with it. You'll probably see it. I think you can already see it maybe, but it's only gonna appear at a certain time and it's gonna disappear. I've got to change those dates, but you're gonna be able to see it. You just
Gotcha.
won't be able to do anything with it until the day of the test.
Okay.
Okay.
All right. Thank you.
All right. See you.
So,
So
Go ahead.
okay, I'm gonna email you because I have a test, another midterm that morning, and then I have to go to work. So I might skip work, but we'll see.
Okay. Well, like I said, if you'd rather go ahead and take it this Tuesday, that would give you this Wednesday, Thursday. That would give you a slight disadvantage of the other students, but I can accommodate you if that would help you. But we could also, since you have another exam, if you want to, I could set it up for you to take at a different time. I just give you a different version of the test.
Okay. I'll email you.
Okay. Thanks, Krista.
You're welcome.
So short wise is midterm has been moved to next Tuesday,
Mhm.
and it is at basically 10 o'clock if I can start there.
Yeah, you should be able to start at least by 10:15.
Okay.
Let's see,
Yeah.
the class hour and 15 minutes, and I need you to have 2 hours. So I'll start at least, I'll allow you to start at least 45 minutes early. Or
Okay.
stay 45 minutes late. Yep. Anybody else? Eliza?
Yeah, I guess for me, since you are moving it till next Tuesday,
Mhm.
I don't know if you were gonna put chapter 27 in it.
Nah, I probably won't. I'm just gonna stick to the one I already made, I think.
Okay. Yeah, because I still have to take a chemistry test by tonight as well. I don't know if you still wanted me to take it either today or if I can, then wait.
Yeah, that respondus test, you try to take that today, even if you don't even put any, you got to put the time in to do the download and all that stuff, but you don't have to put any time in on actually working the problem. You can just take random guesses if you want, because it's going to tell you the right answers. But it's
Right,
important that
but
you get that
the-
part worked out first.
Okay, and then for the actual midterm, since I'm still gonna be on vacation starting tomorrow until the 23rd, I was wondering if,
Yeah, the 23rd is
It's-
that, so we made it the 19th, so we'll just, oh yeah, that's right, I forgot you were gonna take it early, so if you want to take it tonight, you can, but you said you already have a chemistry test tonight, right?
yeah, that was due tonight.
Yeah, I don't think you want to take both those tests at the same time. You get back on the 23rd. In principle, you could take it like the 24th or 25th. I'll just make up a different test for you. But again, that would, that kind of makes for a bum vacation if you're thinking about a test when you get back. But by giving you 2 days afterwards to prep, would that be acceptable?
Yeah, that
Okay.
should be good.
Well, just email me when you get back. That way I'll remember and I'll make up another test and we'll decide on a day. Maybe we'll make it the Wednesday, Thursday, or Friday when you can't come back. Okay.
Okay, sounds good. Thank you, Professor.
You're welcome. See you, Eliza. Kendrick, Patrick, William, anybody? The other William? The other William. Like pork, the other white meat. Hey man, these are the jokes. You're getting cool stuff like this from the chemistry department. All right, it looks like nobody else has anything. They might not even be here, so I'm going to sign off. Have a good one, everybody.